So we discussed today about PageRank, which is one of the metrics that we discussed in the first lecture, but briefly. So today we will try to understand the intuition behind PageRank and why PageRank is useful, and we also look at the limitations of PageRank. Okay. Remember the link analysis metrics that we have discussed so far. Those are useful in the context of node prediction, link prediction, node classification, these kind of tasks, and these are also useful when we want to measure the importance of nodes or importance of an edge. Okay, and PageRank is one of such metrics in which we basically look at how importance of a node flows from one node to another node, and that in turn boosts the importance of the other nodes. Okay. So the history I already discussed in the chapter 1 or chapter 2, but basically the idea here is that let us consider a directed network where a link indicates either some sort of citations from one web page to another web page, or whatever, one scientific paper to another scientific paper, and our task is to measure the importance of nodes. Okay, so let us look at some notations. We use the term forward link to indicate a link from A to B, for example. So there is a link from C to D, and this is a directed graph. This is a forward link. This is a forward link with respect to C, right? So this is page C, this is page D. So with respect to page C, this particular link is a forward link. With respect to page D, this is a backward link. Okay, so outward edges indicate forward links, inward edges indicate basically backward links. Okay, so an importance of a node, right, basically spreads through its outward edges, right, through its forward links. Say for example, the importance of node C would basically move from C to D, from C to F, from C to E, right, and this in turn would increase the importance of web page D, web page E, and web page F, right. So so this is a very simple metric. So basically the idea is that basically the idea is that we assume that the importance of a node basically divides uniformly across its outward edges, and that importance would further boost the importance of the other nodes, and we denote FW. So FW is the set of forward links. Okay, basically nodes. So set of nodes which basically the node W links to. So this is W, and say W is connected to these 4 nodes, say A, B, C, D. So F of W is A, B, C, D. Okay, and similarly we define say E, F, G. So we define something called BW, which correspond to backward edges, right. So BW would be G, E, and F. Remember, FW and BW contain nodes, not edges. Okay. So now if we assume that the importance or a rank, right, or prestige, for example, of node W is RW. Okay. So what would happen essentially is that node W acquires importance or prestige from its from its inward, right, or whatever backward neighbors, right. So W basically receives prestige from E, from F and from G. Okay. So RW is basically of sum of all the backward nodes of W, which is denoted by BW, and small b is one such node. RB is the importance of one of the backward nodes B, and NB is the degree of the backward node B, right. Let us say in this case B is E, okay, and say E has degree 3, and remember this degree NB, so NB is the neighbors, right, NB is the neighbors of B. This is basically outward edges of B. So NB is essentially forward edges, forward nodes. Okay. It means that the importance of node E is equally divided into 3, and one such division, one such component moves from E to W, and that component would boost W's importance, right. This is RW. Now, and we assume that the underlying graph is a connected graph, because if this is not connected, then there are some issues, but let us assume that this is connected. We will see how we can tackle this problem, this disconnected components and so on. Okay. So if there is no hyperlink exists, right, for example, say there is a node W, and node W does not have any inward links. Now remember this node W in this case, so node W acquires prestige, importance from all of its in degree neighbors, inward neighbors, right, incitations. Now if W does not have any incitation, then how W's importance will increase, right. So for those cases, for those pages which do not have any inward, inbound edges, we assume that they have some non-negligible importance, which is 1 by n. What is n? N is the total number of web pages present in the graph. So if there are say 1000 web pages, so all the web pages initially would get 1 by 1000, 1 upon 1000 prestige. Okay. So therefore, for those nodes which do not have any inward edges, they would also get some importance in terms of 1 by n. Okay. So this is an example. So you see that in this graph there are 4 nodes, and let us say this node A, right, it has 3 outward edges, 3 forward edges. Therefore the prestige will divided equally, 1 by 3, 1 by 3, 1 by 3. For B, 2 outward edges, so 1 by 2 and 1 by 2, and so on, right. So now A's prestige is basically 1 plus 1 plus 1, assuming that each of these edges contributes 1 unit of prestige, right. So RA is 3. What is RB? RB has only 1 inward edges, which is only 1 inward edge, and the important it carries is 1 by 3. So therefore RB is 1 by 3, RC is also 1 by 3, RD is 1 plus 1 plus 1 plus 1 by 3, okay, 10 by 3. So these are initial importance, okay. So this is a raw page rank. So raw page rank of node A is 3, node B is 1 by 3, node C is 1 by 3, node D is 10 by 3, okay. What is the normalized page rank? Normalized page rank, we want that the page rank value always ranges between 0 to 1. So what we do after every stage, after every iteration, we take the sum of all the prestige values and we divide each component by the sum. So 3 would be divided by 3 plus 1 by 3 plus 1 by 3 plus 10 by 3, whatever is the number, right, and so on. And then we will see that this would be the normalized page rank. 0.4, 0.05, 0.05, 0.5. You see that the sum is 1. So after every iteration, we make sure that the sum is 1. If it is not 1, then we explicitly make it 1 by divided by the sum, by divide each component by the sum. Okay, and then we repeat the process again. So now for page A, the prestige is 0.4, page B 0.05, 0.05 and 0.5. Okay, then what would happen? We repeat the same process again. Okay, and when we stop when we see that there is no there is no change in the, there is no significant change in the PageRank values of all the pages. Okay, but what is the problem here? So in this approach there are two problems. The first problem is if you somehow reach a place, reach a node which does not have any outward edges, forward edges, what would happen? Right, you basically stop here. You can't move it further. Okay, so this kind of node is called dead end, right? Because this is a dead end. You won't be able to move further. There is no outward edges. There is no forward edges. Okay, so if you follow this process, okay, this kind of process, then after this stage you won't be, when you come here, you won't be able to proceed further. Okay, the second problem is called spider trap. Let's look at this structure. Okay, so you move from this node to this node, and then when you come here, there is only one outward edge, forward edge. So you move through this, you come here, you move through this, you come here, you move through this, come here, and you basically keep on rotating. You keep on rotating, you keep on circulating within this structure. You won't be able to move further. This is also dead end, right? But you are not static here. In case of dead end, you get stagnant, but in case of spider trap, you basically you have got into a trap. Okay, so how do we overcome these two problems? To overcome these problems, we use something called teleportation probability, which we have already discussed, but this name is something which we have not encountered. We will use something called teleportation probability. What is teleportation probability? So in normal cases, what we do, at every node we basically choose one of its outward edges and then we move, and then we basically choose these outward edges uniformly at random, one of the forward edges uniformly at random. This is one probability. So with certain probability you choose one of the outward edges. With the other probability, 1 minus the given probability, say with probability P, you choose one of the outward edges. With probability 1 minus P, you can jump from one node to any other nodes in the network. Okay, say for example you are here. So with probability P, you can choose this edge. With probability 1 minus P, you can move from this node to any other nodes in the network. You can directly jump from this to this, for example. Although there is no direct edge, right? And this is called teleportation probability. So every node, at every node, you have two chances. One chance, you essentially sample one of the outward edges, right? One of the forward edges. In other probability, you basically jump from that node to other node. Okay. Therefore, when you start here, there would be some probability, some chance that you get out of this node, right? Similarly, when you trap here, there is some probability you get out of this node, out of this structure. And this is called teleportation probability. So through this teleportation probability, we keep the random walk process going. Okay. So So this is the idea. And what is the teleportation probability? Teleportation probability is uniform. It's 1 by n for all the nodes. Also you can make it different depending on your applications. We will discuss some variations of PageRank like personalized PageRank, right, topic sensitive PageRank, where you can set this teleportation probability based on your need. Okay. So now let us look at the combined PageRank equation. So this part we have already seen, right, and what is this E? This E is basically a vector, right, which contains teleportation probability. So in this case, since we assume that all the nodes are equally likely to be jumped to, so this E would be 1 by n in our case, in this particular case. So we have this probability and this probability. This is choosing one node, one of the forward nodes uniformly at random, and this is jumping from the given node to any of the nodes, and these two things are controlled by this parameter alpha. This alpha is called a damping factor, right? And we make sure that after every iteration the PageRank value would be 1. The sum of the PageRank values would be 1, right? And therefore, of course, the PageRank of individual node would be between 0 to 1. Okay. So this damping factor alpha, right? I mean, people basically consider 1 minus alpha as a damping factor. So damping factor D is equal to 1 minus alpha, but doesn't matter. I mean, alpha and D, they are basically kind of same, right? So generally we set D as 0.85. There is no theoretical reasons behind this, but empirically it has been, historically it has been set as 0.85, right? Now you can easily relate it to random walk process, as I mentioned in the last day, that you essentially start from a particular node and you are basically a random walker. You follow one of the outward edges, or you can jump from one node to any of the given nodes, and so on and so forth. You keep on doing this thing until unless things get stable. Now what do you mean by things get stable? So when you keep on doing this thing in terms of matrix operation, for example, in random walk, now you can basically map the PageRank process using a Markov process, right? In the Markov process, what happens? There are states, Markov process. I am not going into details of this, but if you are interested, you can look at it. In Markov process, depending upon the depending on the degree, if it is 0th order Markov process or 1st order Markov process, 2nd order Markov process, the prior would be different, right? But let's assume that it's a simple process where nodes are states, and you can basically move from, so the states are connected through transition probabilities, right? So you can move from one node to another node through this transition edges with certain probabilities. See, here also you can think of web pages as different states and hyperlinks as this edges through which a transition is possible. So in the steady state, there is something called steady state probability. Steady state probability. At the steady state probability, what happens is that the ranking of web pages would not change further. You keep on iterating the process, it would not change further. The normalized version, okay. So at the steady state probability, as a steady state stage, you get whatever probability you get, that would be your PageRank, okay. So a variation of a PageRank is something called personalized PageRank, okay. What is personalized PageRank? So in case of PageRank, we assume that a random walker can jump from that node to any of the nodes, okay, in the system. It may happen that you do not allow the random walker to jump to any of the nodes. You set a set of nodes, you fix a set of nodes and say that, hey, if you really want to jump, you can only jump to these nodes, this set of nodes, any of the, one of these set of nodes, right. So, therefore, the teleportation probability 1 by n that we mentioned earlier would not remain as 1 by n in this case, right. So, what would happen? Say there are n number of nodes, out of them p number of nodes, p number of web pages have been selected by you, and your random walker can only jump to one of these p web pages, right. Remember, there are two possibilities. One possibility, you can follow one of the outward edges, and the other possibility, you can jump. Now, when you want to jump, you can't jump randomly. You can jump to any of the predefined set of pages. Okay, and this predefined set of pages are already selected based on the topic, right, based on the application, for example. So, for these pages, for this set of pages, it would be uniform. It would be 1 by mod p or 1 by p, say. And for other n minus p nodes, it is 0. So, when we write this E, right, this one, this would be, is a vector, it would be 0, 0, 0, but 1 by p for those pages which have been selected, other would be 0. Okay. So, now you see this set of web pages HW, this, for these cases your jumping probability, teleportation probability will be non-zero, for other cases this would be 0. Okay. So, this is called personalized page rank, because you are essentially making the entire page rank process personalized, right. You are giving preference to a set of web pages for which you want your random walker to come again and again. This is also called biased page rank. This is also called topic specific page rank, because the set of pages that we are going to choose, these are based on the topics which you are interested in. For example, say you are running the page rank algorithm on the citation network, and you want that your random walker would basically jump again and again to the scientific papers related to AI. Okay. So, you basically ignore other papers and you give more weightage to the paper related to AI. This is also called topic specific page rank. It may happen that this set SW, right, or this P set, this contains only one page. Okay. So, what you are basically saying, that either you choose one of the outward edges, forward edges, or you jump, right. So, this is called random walk with restart, random walk with restart, RWA. Okay. So, the idea is that when you say you start from a particular node and you only allow your random walker to jump to that node, right. So, the random walker is not allowed to jump to any other nodes. It can only jump to the seed node from which you have already started your random walk process. So, in that case, what would be the value of E? All the nodes, the values of all the nodes would be 0 except the one from which you start, and for that it would be 1. Okay. This is called random walk with restart. Now, random walk with restart will be very important. We will discuss later stages. It is very important when you when you understand the importance of a node with respect to its contexts. So, you do not want your random walker to move out of the context. Either you move through the context or you jump to the initial node. Okay. Now, what's the advantage of PageRank kind of method? The advantage is that you easily vectorized it, because ultimately you deal with matrix and vectors, right? It is guaranteed to converge to a unique solution. That is also good. You can actually pre-compute PageRank initially for a web graph, right? And this PageRank value would act as an initial prestige for a PageRank for a particular web page, and then depending upon the content or query, you can further modify. But the initial ranking can be obtained using PageRank, right? And the other other advantages is that it may be considered as a robust metric, because it all depends on the inward edges, right? You are moving, because if a node has more inward edges, its importance will increase. So, inward edges is something which is difficult to manipulate. So, therefore, this is kind of a robust. The disadvantage is that since it is not dependent on the content of the web page, one can actually create a crap web page with spam content and add a lot of such hyperlinks and take part of the decision process. Okay. The second problem is that, PageRank is mostly useful for static graphs. Okay, although its variations have already been proposed, but mostly it is useful for static graphs. If the graph changes over time, you need to compute PageRank again and again, right? You can actually, although I mentioned that this is robust, but there are some ways you can hack it. For example, you create a lot of web pages, for example, and these web pages are linking each other like this, right? It's also kind of a spider trap, but now the size of the spider trap is huge. So, when your random walker comes here, right, it basically keeps moving within your collusive network, okay, within your own gang. Automatically your page rank will increase. Okay, this is another such problem of PageRank. The other PageRank problem, the other limitation of PageRank is that it gives importance to nodes which are kind of redundant. For example, think of a network like this, right? Something like this. Okay. If you run PageRank, what would happen is that maybe this page will be ranked first, this would be second, this would be third, this would be fourth, this would be fifth, and so on. If you look at the first 4 web pages, they are very close by, they are nearby, right? So, the amount of information that you can obtain from each of these nodes will be same, right? For example, you basically want to get diversified information from a network, right? So, if you run PageRank on this kind of network, you will get these 4 nodes as top nodes. But these 4 nodes are part of the same context. There is no need to return 4 nodes. You can only return 1 node, and that node would basically give you ideas about this page, this particular portion. Instead of this, if you return 1 node from this component, 1 node, say this one, and this node, these 4 nodes, at these 3 nodes, at top 3 nodes, then you basically cover the diverse parts of the network. So, diversity is not guaranteed in case of PageRank. So, we will discuss another metric called DivRank in the next lecture, which basically takes care of both the importance as well as diversity. Okay? Thank you.